It's integral time! So let's do integrals. Okay, first thing we're looking at is just our ideas, basics, Riemann sums, derivatives of integrals, initial value problems, differential equations, and volume. We're not going to get through all of this just in one video because that would take, like I've said before, 47,000 minutes. We're pretty much just going to live in this region today, in this video here. So let's go ahead and get started on it. The Riemann sum, it's basically using rectangles to approximate the definite integral, which is the area between the curve and the x-axis. We've got our left, right, midpoint, trapezoidal. You guys are all pretty good at these, so I'm not going to go through and read these different types, but you're more than welcome to. Then we've got our infinite Riemann sums, and those are the actual value of the integral, and they involve limits and summation notation, which you guys always are like, what? And then I do it, and you're like, oh. So let's do it. That way you get the oh part of the moment. So remember, the integral is the same as the limit as n goes to infinity, the sum k equals 1 to n of f of a plus delta x, k delta x, let me sneak that in there, times delta x. And that doesn't look like k delta x, does it? K delta x, that looks better. So the way we get delta x, though, that's b minus a over n. So for us, that's going to be 5 minus 3, or 2 over n. So then a plus k delta x is equal to 3 plus 2k over n. So this underlined part here is going to end up being 3 plus 2k over n to the fourth, not to the n, times 2 over n. So now I'm just looking for which of these sums has that. Well, that would be b. So the definite integral is that sum. And I've told you guys before, if you are given the limit and asked which one of these integrals, so like all the multiple choice answers are integrals, I would recommend taking those integrals and rewriting them in the limit notation and see which one matches. That's because there's so many different ways that you could rewrite the limit and it would be right. So it's more consistent if you start with the integral and go to the limit. Okay. We've got Rochelle again. Rochelle was very busy apparently. Use a left Riemann sum with 4 subintervals indicated by the data in the table to approximate the integral from 0 to 9 of rt dt. Using correct units, explain the meaning of the integral from 0 to 9 r of t dt in the context of the problem. Okay, we're doing a left Riemann sum, so let me do that up here. It's not quite work out how I wanted it to. There we go. I'm still not happy. I guess I'll just zoom back out. So we're doing a left Riemann sum. That means we're going to start at the left side. We're going to take that 72, and we're going to keep it for 3 minutes. Plus 95, and we keep that for 2 minutes. Then we've got 112 that we keep for 1 minute. And then we've got 77, which we kept for 3 minutes. So we just start on the left side of the interval. We got 72 times 3, that's 216, plus 95 times 2, that's 190, plus 112, so 216 plus 190 is 406, plus 112 is 318, plus 77 times 3 is 231. Who am I trying to impress? I'm just going to get a calculator. BRB. While I was looking for my calculator, I remember this is the no calculator section, so I will continue and get 749 rotations. So I recognize that this is a little computationally annoying, but I believe in you. You guys are great. You're going to be able to do that just fine. Okay, so there's part of the question. It says, using correct units, explain the meaning of the integral from 0 to 9 r of t dt in the context of the problem. So I'm going to do that up in this corner where I can get some extra space. The integral from 0 to 9 r of t dt is the number of rotations completed on the interval (0 to 9). Oh, got a little crazy there. There we go. The integral from 0 to 9 rpt is the number of rotations completed on the interval 0 to 9. That's the rest of the problem. Okay, let's look at our next idea. We've got our basic integrals. Anti-differentiate, plug in the bounds, and simplify. No bounds, don't forget to add c, lest your house gets burned down. And then don't forget to change the bounds when we're doing those u sub on those definite integrals. Also, if you have to use u sub on an indefinite integral, one that doesn't have bounds, don't forget to substitute back in your original expression for u. Let f be a continuous function defined on the closed interval (-1 to 4). The graph of f consisting of 3 line segments is shown above. Let g be the function defined by g of x equals 5 plus the integral from 2 to 4, or 2 to x, f of d dt. We want to find g of 4. Okay, so this is not one of those anti-differentiate situations. What we have to do is recognize geometrically what's happening. Remember, the definite integral is the area between the curve and the x-axis. So area between the curve and the x-axis, just break it up into some shapes. So I'm going to find g of 4. That means that I need to find 5 plus the integral from 2 to 4 g f of t dt. Okay, so I'm looking for that because g of x is defined as the integral from 2 to x. So if I'm looking for g of 4, that should be the integral from 2 to 4. Okay, so then I've got this region here, and I've got all of this as well. Okay, the area of that is going to be 1/2, but it's below the x-axis, so remember that's going to be negative. And then this space here, that area is going to be 2. So I just found the area of 2 triangles. So this is 5 minus 1/2 plus 2, so that's 6.5. So just use geometry. Okay, the function f is continuous for (-4 to 4). The graph of f shown above consists of 5 line segments. What is the average value of f on the interval (-4 to 4)? Well, I've got answer choice of D cut off, but don't worry, that's not the right answer. Average value, remember that's the 1 over b minus a thing. So I'm going to have 1 over 4 minus (-4), the integral from (-4 to 4), f of x dx. Now again, they didn't give me a function to anti-differentiate, so I'm just doing this all on area. So here's a triangle. The area is 1. Here's another triangle. That area is (-3). Negative because it's under the x-axis. Now here, I've got, oh, how'd that happen? Whatever, I'm going to keep drawing, see what happens. It's not working. There we go. I've got, what I'd probably do is I'd notice this little triangle, this little triangle, this little triangle, and then these 2 squares. So that's going to be 3.5. So 3.5 minus 3. 3.5 minus 3 is going to be 1/2 plus 1 is 1.5. So this becomes 1 over 8 times 3 over 2, which is 3 over 16, which is B. So again, another geometric problem, just break it into shapes that you know. Okay, let R be the region in the first quadrant bounded by the graph of G, and let S be the region in the first quadrant between the graphs of F and G shown in the figure above. Region in the first quadrant bounded by the graph of F and the coordinate axes has area 12.142. Function G is given by g of x equals bleh, and the function f is not explicitly given. The graphs of f and g intersect at the points 4 and 0. Find the area of S. So I'm looking for this space right here. So this is the area between curves. Remember when we do area between curves, that's the top function minus the bottom function, and then we just integrate. So what I need to do is the integral from 0 to 4 for f of x minus g of x. Well, they didn't give me f of x, right? Well, what I can do is I can split this integral up. This, they actually did give me. Right here it says the region in the first quadrant bounded by the graph of f and the coordinate axes has area 12.142. That means the integral of f from 0 to 4. So that is going to be 12.142. The other integral I'm going to get out of my calculator, which I have yet to do. So let me go do that real quick. Integral from 0 to 4 for square root x plus 6 cosine pi x divided by 8. So that becomes 12.142 minus 6.938. And that's 5.204. Hooray! So this is on the calculator section. Obviously, that g of x function would be horrible to integrate. Just make sure you write what I've written down. That shows your work, shows you know what you're doing. If you just write 5.204 because you did all the work in the calculator, you just missed out on a bunch of points. You only got the 1 point for the answer, whereas this integral could be worth even 2 points. So make sure you actually write down this information that you're doing in the calculator. All right, derivatives of integrals. We do this all the time on the test. This is that thing where you get a free point just for writing g is f prime or something to that effect. So remember, derivatives, to do an integral, we do an antiderivative. So if I take the derivative of an integral, aren't I taking the derivative of an antiderivative? They should cancel each other out. So that's where I'm just going to plug in the variable into the function. Now, if the variable's on the lower bound, remember we have to switch the bounds by multiplying by -1. Or if the variable's not just x, it's like x cubed or sine of x, then we need to multiply by the derivative of that bound as well. It's not as simple as just shove it in because we've got to do a little chain rule. So, oh, perfect. I see one immediately. Okay, so I need to find f prime of x before I can find f prime of 2. So I see that that is not just an x in the upper bound. So what I'm going to do is I'm going to take that x cubed, and every time I see a t, I'm going to put x cubed. So I've got 1 over 1 plus natural log of x cubed. But I also see that is not just an x in the bound. That's an x cubed. So because of chain rule, I have to multiply by the derivative of the upper bound. Now I just plug in the 2. 2 squared is 4 times 3 is 12 over 1 plus ln of 8. So D. Hooray! Do another one. Oh, look, this thing again. Let f be a continuous function defined on the closed interval -1 to 4. Okay, we've done all this setup before. On what intervals is g increasing? Justify your answer. Okay, think back to derivatives. We did the derivatives video. G would be increasing when g prime is positive. So let's look. Let's look at the definition of this g of x. I'm going to see g prime of x is equal to, well, the derivative of 5 is 0. And now I've got the derivative of an integral, so that's just f of x. I got a point just for writing that. So now I need to find when g prime is positive, which is the same as finding when f is positive. Well, f is positive here, and f is positive here. So from -1 to 1 and 3 to 4, because f of x is greater than 0. So saying g prime of x is f of x, then I can say because f of x is greater than 0. That's all there is to it. This should be pretty easy points because it shows up pretty regularly on the exam. Oh, look, it's this thing again. On the closed interval, -1 to 4, find the absolute minimum value of g and the absolute maximum value of g. Justify your answers. Okay, so what I need to do, I've got a closed interval. I need to find the absolute min and the absolute max. That's candidates test. I'm going to plug my endpoints and my critical points into the original function. So I've got the endpoints, -1 and 4. So remember, we got to make this table. but I need to find the critical points as well. So remember, g prime of x is f of x. So whenever g prime of x changes sign, I have a critical point. So whenever f changes sign, I've got a critical point. That happens here and it happens here. So I'm also going to check x equals 1 and x equals 3. So we've done g of 4. If you remember a couple slides back. Right here, g of 4 was 6.5. And yes, I literally did just slide back so I wouldn't have to do it again. And now it's biting me. It's fighting me. Okay, so this is 6.5. Okay, now to get g of -1, I'm going to do the same idea that I did before. I'm going to do g of -1 equals 5 plus the integral from -2 to -1 for f of t dt. That looks like f of star, but it's meant to be a t. Okay, so I need to find the area between, that should be a positive 2. I need to find the area between the curve and the x-axis on the interval 2 to -1. Now, keep in mind, I'm going backwards. I don't know if that turned out to look backwards to you guys, but I'm going backwards. I'm starting at 2 and going backwards. So whereas this is normally a -1/2, I have to change the sign because I worked backwards. So this is a +1/2. And whereas this would normally be a +2, it's actually a -2 because I'm going backwards. So that integral ends up being -1.5. So this is 5 minus 1.5. So g of -1 is going to be 3.5. Okay, now to get f of 1, it's kind of the same idea. Or sorry, g of 1, that's kind of the same idea. I've got 5, I'm starting at x equals 2, going back to x equals 1. This is going to be a +1/2 because I worked backwards. So 5 plus 1/2 is going to be the 5.5. Okay, now when I go from 2 to 3, I want this thing. I'm no longer going backwards, so then it in fact is a -1/2. So then I'll have 5 plus -1/2, so that's 4.5. So there's my min. And there's my max. And this is the work that I've shown is sufficient justification. I know I went through some of those integrals kind of fast, but they all model the same idea that g of -1 and g of 4 did. Just make sure that if you're going backwards, then you have to change the sign of your area. Okay, let f be a continuous function. Oh, look, it's the same thing again. Let h of x equal x times g of x, find h prime of 2. Well, that means I need to find h prime of x, right? I've got a function times a function. I've got x times g of x. So I need to use the product rule. So 1 times g of x is the derivative of the first times the second, plus the derivative of the second times the first. So if I want h prime of 2, that's going to be g of 2 plus 2 g prime of 2. Well, remember, g prime is just f, and g prime of 2, then if I look at the graph of f, is -1. So this becomes -2. G of 2 is going to be equal to 5 plus the integral from 2 to 2 for f of t dt. Well, remember, when the bounds of an integral are the same, this ends up being 0. So g of 2 is just 5. So then 5 minus 2 is 3. And that's the answer. Did I finish? Nope. I've got 2 more. All right. Let's get these last 2 done. That way we can wrap up this integrals video. The graph of a differentiable function f is shown above for -3 to 3. The graph of f has horizontal tangent lines at x equals -1, x equals 1, and x equals 2. The areas of regions A, B, C, and D are 5, 4, 5, and 3, respectively. Let g be the antiderivative of f such that g of 3 equals 7. So g is the antiderivative of f, which again means g prime equals f. So g double prime would equal f prime. So in order for g to be concave up, I need g double prime to be positive. It means I need f prime to be positive. And if f prime is positive, that just means f is increasing. So I just need to find where f is increasing. Well, that's -1 to 1 and 2 to 3. So -1 to 1 and 2 to 3 because f is increasing here. Okay, so we had a lot of logic going on there relating derivatives and integrals, but that's kind of the nature of these FRQs.